Okay, so today I'm going to cover an important result in mechanism design, and so the so it's an extension of Meyerson's optimal auction result, but it's a very stark result in the sense that you will see that the seller gets a lot of advantage by extending Meyerson's model into this informational environment. Okay, so the paper that I will mostly be talking about is this paper by Kremer and McLean. Uh, it's a paper published in 1988. They have a follow-up paper on the same similar topics, which has some extensions of this also. But this is the important paper. So the main difference between this paper and Meyerson's paper is that buyers' values may now be correlated. Remember, Meyerson's analysis assumes that types are independently drawn, and that plays an important role both in the characterization that we established for incentive compatibility, but also in the subsequent optimal auction analysis, right? So it's not clear how one can design an optimal auction if types are correlated. Okay, and of course, correlated types is maybe an appropriate assumption in various settings. So, in particular, I have this example which is often cited in the literature that government sells oil fields or coal fields or things like that, and the value of the oil field is not known to everyone, and each bidder may conduct its own tests about what the uh, estimated value of the oil field is, but it's quite likely that the test results are going to be correlated, right? So every bidder will have get some estimate, but these estimates are going to be correlated.
So, sir, in a sense, the correlation may result in lower information rent. We were talking in last class.
That's correct. Okay, so basically that you will see at the end of this talk that the information rent will be reduced. Okay, so you'll see how exactly that happens. Okay, so the main question is, does the presence of correlation in types significantly change Meyerson's result? Okay, so that's going to be the objective of the lecture. So the model is basically a seller is selling a single object and she has no value for the object. And the question is, what mechanism maximizes expected revenue of the seller if the types of buyers are correlated? Of course, we know that the benchmark here is that in complete information environment, the seller can extract full surplus by asking highest buyer a payment equal to value. So if the seller knew all the values perfectly, then she would just approach the highest valued buyer and ask her to pay the highest value. Okay, and the buyer has every incentive to accept that particular offer. So in that sense, it can extract the entire surplus. With incomplete information, we saw from Meyerson's analysis that this is not quite possible. You always have to pay some information rent to these buyers. Okay, so you can't extract the full surplus. But what we are going to show in this lecture is that even if you have incomplete information, if the types are correlated, you can still extract full surplus in expectation. Okay, the expected full surplus can be completely extracted by the seller. Okay, so that's what we are going to show. And of course, the delicate thing here is what is the nature of correlation which allows for this full surplus extraction. Okay, and so that's what the paper is going to flesh out exactly the nature of correlation which can allow such full surplus extraction. Okay, the main insight of the paper is what is now known in the literature called the Kramer-Maclean lottery. So Kramer and Maclean basically introduced this idea of a uh, participation fee, which can be thought of as a lottery given to the bidders before they participate in the auction. Okay, so here is how they think about the mechanism which can extract all the surplus. So remember, the seller can always do a Vickrey auction and get expected second highest value as revenue, right? So if you conduct a Vickrey auction, what is the revenue that the seller gets? Well, the seller gets a revenue which is equal to the expected second highest value, right? Because the Vickrey auction payment is the second highest value in every type profile. So the Kramer-Maclean question is, can the seller get expected highest value as revenue? Right? So when we are talking about extracting surplus here, we mean to say that in the Kramer-Maclean sense, it will be the expected full surplus. And what is the expected full surplus? It is the expected highest value. Okay. So at each type profile, the seller gets a surplus, or the mechanism can get a maximum surplus equal to highest value of the profile, and the expected highest value is the expected surplus, the expected maximum possible expected surplus that the seller can hope to achieve. Okay, and uh, the Kramer-Maclean solution is that on top of the Vickrey auction, you introduce a participation fee to every bidder who is participating in the Vickrey auction. Okay, so you not only conduct a Vickrey auction, but also before every bidder enters the Vickrey auction, you ask them to pay a participation fee. Okay. So the clever insight is that this participation fees can be designed in a careful manner such that incentive and participation constraints are maintained. Okay. So first, before I get to what the Kramer-Maclean participation fee is, let's first consider the following participation fee. So we know that we can, before everybody reports their type or even realizes their type, the seller can always compute the expected highest value and expected second highest value. It can always compute that, right? That's just based on the priors. Based on the priors, what is the expected highest value and what is the expected second highest value? Okay, it can always compute that. So what we will ask the buyers to pay as participation fee is equal to 1 over n times the difference between the expected highest and the second expected highest, or expected second highest. Okay, so if you ask everyone, irrespective of whether they win or lose, to enter the auction house, they have to pay this particular participation fee. Okay, if you ask them to pay this participation fee, remember the total participation fee that is collected is basically expected highest minus expected second highest. And the total expected revenue from the Vickrey auction is expected second highest. So basically the seller gets expected revenue equal to expected highest. Okay. So essentially, by introducing this simple participation fee, uh, the seller can extract all possible surplus. Is that clear?
This result is under correlation.
So this result does not require even correlation, right? So I can always do this. So there is no issue about correlation, because if you ask people to pay a participation fee, it does not change incentive constraints, right? The Vickrey auction with a participation fee is also dominant strategy incentive compatible, right? So it won't change incentive constraints.
Payment at type 0, will that change?
Yeah, so everybody will have to pay this constant participation fee. So even the lowest types, the type which has zero probability of winning, will also have to pay a participation fee.
In that case, payment at type 0 will be greater than 0, or maybe greater than 0, may
Yeah.
not be less than equal to 0.
So payment at type 0 would be strictly greater than 0 because this participation fee is strictly greater than 0. Yeah. So
And it
that,
violates IIR.
yes, so that's what I have said in the last bullet, that basically we can always charge such participation fee, but it will result in participation constraint being violated. Right? So, so here, for instance, as you pointed out clearly, that the lowest type will also have to pay a participation fee, but he has zero probability of winning. So basically, his payoff is negative. Okay. So, so the trick is to, so the question is then, is there a more sophisticated participation fee that we can impose such that the IR constraints are also satisfied? Okay. So that's what the innovation of this Kramer-McLean lotteries are. Any questions? Great. Okay, so the Kramer-McLean lotteries are of the following type. So remember, when a buyer is trying to report,
Sir, I had a small question.
yeah,
The participation fees is declared before the types are for the agents or after the types are revealed?
no. So this is a mechanism, right? So it's a direct
Uh-huh.
revenue mechanism. So basically, you will have to declare before everyone reports what you will
Okay.
do in the mechanism. So in
Okay.
particular, you will say that uh, uh, everyone pays this much of fees, and based on your report, I will decide how much, who gets the object, and how much will they have to pay.
So the agents know their type anyways, so they will decide if they want to participate or not.
Yeah.
Okay.
Right. So basically, I mean, you can think of this participation fees as something which is part of the payment of the mechanism itself, but it's a component, at least in this kind of fees that I have talked about. It's a component which is independent of the types of the agent. Okay, so the participation fee that I'm talking about here is something which is independent of the types of the other agents, so they can be charged even before the types are realized by the agents. Okay.
Oh, okay.
But in principle, I can also say that, okay, you come to the auction, but I will take something from you which may depend on the types of everyone, independent of whether you win or lose. So that can be basically a type contingent participation fee.
Okay.
Okay. Right. So the key is to design participation fee such that the expected participation fee equals expected payoff of buyer in the Vikri auction. Right. So if as a designer, I'm still thinking about the Vikri auction supported by a participation fee. If I can design a participation fee such that the expected payoff in the Vikri auction of the bidder is exactly equal to the expected value of the participation fee. Okay, then the expected payoff of each bidder is going to be zero, and the seller can take all the surplus. Okay, so so today's lectures, I'm going to tell you how Kramer-McLean go about doing it. So the first thing is, why can't we do this for independence, right? So the main idea here is that uh, you know we cannot do this for independence because of these 3 points. First, participation fee can only depend on others types. Okay, so as you'll see, to maintain incentive compatibility of the Vickrey auction, participation fees can only so agent I's participation fee can only depend on types of other agents and not his own type. Okay, so you'll see that in a minute. Other else incentive constraints get messed up. Second thing is, if the first thing, you buy the first thing, then basically expected participation fee is independent of the type of an agent. Okay, so how much participation fee you will pay, okay, it's independent of your own type. Okay, it may depend on others types, right? But I mean, how the other types are distributed and so on and so forth, but it can never depend on what your type is. Okay, but remember, expected payoff in the Vickrey auction will depend on my type. Okay, so if I am of a high type, my expected payoff is higher. If I am low type, my expected payoff is lower, right? So which means that if I were to maintain this constraint that expected participation fee must be equal to the expected payoff of each buyer type, that will be impossible to satisfy, uh, and so hence interim IR will be impossible. So that's so with independence you run into this problem. Okay.
With independence, why can't we have the expected participation fee independent of type?
Yeah.
Because even in that case, it can be a function of t minus I.
Yeah, it can be well, it can be a function of t minus I, but then when we take the expectation, it's no longer a conditional expectation, so it's independent of my type.
Okay.
Right, so basically when I'm expecting out this participation fee always depends on others types. That's what the first point is. But when we compute this expectation is no longer a conditional expectation because types are independent. So if my type is high, my expected participation fee will not be different than when my type is low, right? Because the types are independent. So my type does not influence the distribution of types of other agents. So this expectation, the second bullet expectation, is no longer a conditional expectation.
Okay, sir.
Okay.
And sir, why we are taking benchmark case to be Vickrey auction, and
Yeah.
why not the optimal auction of the last class?
Right. So I mean, it's possible to take any auction as a benchmark. The reason Vickrey auction is taken will be clear in a couple of slides. First thing is that if you're interested in extracting full surplus, we should allocate the object to the highest valued bidder all the time, right? Because if you don't sell the object like we do in the optimal auction at some type profiles, then at those type profiles, we are not generating enough surplus anyway. So there is no hope of, extracting full surplus. So in some sense, what I'm arguing is, uh, if you're hopeful of a full surplus extraction, you better do an efficient auction. Okay, that way you generate the maximum possible surplus, and then you can think about redistributing that surplus through participation fee or some other means. Not redistribution, but extracting more of that surplus.
Okay.
All right, so the model is the same as Myerson, except how the priors look like. So there are n buyers, Each bias type is her value. I'm going to call it VI in this talk. So one main difference from Meyerson's analysis to this one is that the type space is finite. So each buyer draws its type from some finite set capital VI. Okay. So we'll use the standard notation. Capital V is just the product of the type spaces of all the agents, and this V1 to Vn can be totally different type spaces. Okay, so some agents may have high types and some agents might have low types. That won't matter. So whether agents are symmetric or not symmetric. Okay. So now the each type profile or value profile, uh, is drawn with some probability pi v. Okay, so this is a joint distribution now, and we will be interested in this conditional probability, which is the probability that if agent I has type vi, then what is the probability that others have v minus I? Okay. Okay, so our notion of incentive and IR constraints are as follows. So we'll require that our mechanism is dominant strategy incentive compatible, but our participation constraint is interim IR. Okay, so two comments. First is that we can weaken dominant strategy to Bayesian incentive compatibility also. And I'll tell you what happens in that case. The second is that we can strengthen the IR constraint to exposed IR constraint. And we'll see what happens in that case also. Okay, so either you can weaken the IC constraint or strengthen the IR constraint. This choice of IC and IR constraints are motivated uh, by the particular mechanism that is being used in the paper. So the mechanism used in the paper is indeed dominant strategy incentive compatible and satisfies interim IR. So let's stick to this for the moment, and I'll comment on what happens if we change these things. Okay, so we all know what these constraints are. So I'm going to call a mechanism Q and P in this lectures. This is different from the earlier lectures where I was calling small f and small p, but I think it's good to change the notations here so that you can independently look at these slides. Okay, so a mechanism is a pair, capital Q and capital P, and capital QI is the allocation rule for buyer I, and capital PI is the payment rule for buyer I. Okay, and dominant strategy basically says that truth telling is a dominant strategy. Interim IR is saying that the expected payoff of each buyer type is greater than equal to 0. So how do we compute it? Let's go over this one more time. So this is the payoff at type profile VI V minus I for buyer I with type VI. The probability of other buyers having type V minus I conditional on him having type VI is this. So this is the expected payoff he can have when his type is VI. Okay. So the interim IR just requires that every buyer of every type has non-negative payoff. Okay. So exposed IR would have just meant that this bracketed term is greater than equal to 0 for every VI and every V minus I. But we are not requiring that. Okay. So in the paper, they call V and pi a information structure. So basically, this is the information that the designer needs to know before it thinks about mechanism design. So the mechanism designer needs to know the type space or the profile of type space. and the prior on the type space. Okay, so this is what is called the information structure of the mechanism design problem in this setting. So we're going to say that an information structure admits full surplus extraction if there exists a DSIC and interim individually rational mechanism QP such that this constraint holds. So this constraint verbally, it basically says that the expected payment collected by the seller, which is the left-hand side, is equal to the expected highest value from the mechanism. Okay, so expected highest value that can be achieved. Okay, highest expected, highest possible surplus that can be generated.
Basically, at each type profile, you extract the max of VI.
Right. So basically, so at every type profile, the maximum that you can extract is a max of VI. The probability of that particular type profile is pi of B. So the expected high surplus that you can extract is the right-hand term. And the left side is at each type profile, this mechanism, you are generating a revenue equal to sum of PIV, and this is the expected revenue that you're going to generate. So the expected payment of buyers must equal expected highest value. That's what this is saying. Okay. So if there exists such a mechanism given this type space and this prior, then we'll say that this information structure admits full surplus extraction. The vague reasoning that I gave here basically says that if pi is independent, okay, then such an information structure does not admit full surplus extraction. Okay, so that will be a corollary of our result, but that's something to keep in mind. So there are priors for which full surplus extraction is impossible, and we are going to show that there are priors for which full surplus extraction will be possible also. Any question?
When priors are independent, the best a seller can do is the optimal auction we did in the last class. That much extraction can be done only.
When priors are independent, yes.
Yes.
Yeah, exactly.
Okay.
So we are extracting the full surplus in expectations and not necessarily the point wise.
Not point wise. Right. So point wise would have meant that sum of PIV is equal to max of VI, which is not possible unless you have full information.
Okay, so it's not true that at every type profile we get the maximum.
No. As you will see that's not going to be true.
Sir, but if at every type profile we are not getting the maximum, then expectation will be less than the maximum.
No, not necessarily. At some points we'll extract more.
Is it possible that we can extract more?
Yes.
Because
so that's why remember that we are not imposing ex post IR.
okay, sir.
We can extract more at high probability sets and less at other sets.
Yes. Okay. So what are the questions and what kind of answers are we going to get? So the questions are, what information structures admit full surplus extraction? And more concretely, you can ask that if a particular information structure admits full surplus extraction, then what kind of mechanisms can be used? Okay. So that's going to be one of the questions. I mean, two main questions. And basically the answers will be that at least in the finite type space model that we are looking at, there is a sufficient condition on the correlation, basically, which is called the full rank condition, that this paper will provide. Under that, full surplus extraction will be possible. So we'll give you a sufficient condition on the extent of correlation of the prior such that full surplus extraction is possible. Answer to the second question, we'll also give you a concrete mechanism which can extract that surplus, which is a Vickrey auction with a participation fee, which depends on the types of other agents. Okay, so this participation fee, when the bidders are trying to participate in the auction, they don't know exactly how much they will pay because the other bidders haven't revealed their types. Okay, but they will have to make a decision of entering the auction by only knowing their own type and forming expectations over others' types. Okay, so that would play a key role, because now with correlation, this expectation would depend on what your own type is, and we are going to play with this correlation to extract this full surplus.
Sir, where the infinite type space goes wrong in this analysis?
You will see. So the infinite type space, I'll make comments towards the end, but yeah, so analysis is much more complex with infinite type space. Okay, so first thing is, if I'm interested in full surplus, basically efficiency is somewhat required. I mean, this is not a full tight argument, but if you were to think about it, we must allocate the object to the highest value buyer almost everywhere if we were to realize full surplus, right? So efficiency is kind of required, but we kind of know that if I'm insisting on DSIC and we want efficiency, then I have to use some form of a Groves mechanism, right? This is what we have learned earlier, that DSIC and efficiency would mean that I have to use some form of Groves mechanism. So let's remind ourselves of this Groves mechanism, what the payments look like. So remember, in a Groves mechanism, the allocation rule is that the highest valued bidder gets the object, and the payment is given by this particular formula, which is there is this HI function which depends on the types of the others minus the sum of values of the other agents. Okay, so what is the value, expected value, sum of value that other agents are getting? So does everyone remember this? This is the gross payment. So let me pause for 2 minutes just to put my charger on the laptop. Just hold on for a minute. In the meanwhile, keep looking at the Groves payment formula. Okay, so very vaguely, what we know is that if we want to use a if you want to extract full surplus, we may as well use a Groves mechanism, okay, whose payment looks something like this. So what I'm going to do is do a simple trick. So here this HI V minus I is a function of the types of the other agent. So I'm going to define another function which I'm going to call Ri V minus I. This Ri V minus I is basically hi v minus I minus max of j not equal to I vj. So this is like the second highest value. Okay. So so if you do this conversion, then basically I can always write this gross payment is equal to Ri v minus I plus max of j not equal to I vj minus this term, right? So basically I have here added plus max of vj and subtracted minus vj. Okay, so that will basically give you this particular simplification. The idea here is that if I write the hi function like this, then I have this ri v minus I plus this term, which is the uh, payment of the bidder in the Vickrey auction, right? Because what happens if I is the highest valued agent in the gross mechanism, the bidder wins, and basically this term is 0, and this is what he will pay in the Vickrey auction. Okay, max of Vj plus this Riv minus I. Okay, which we are free to choose in a gross mechanism. Okay, if I is not the winner, then she pays Riv minus. Okay, so this Riv minus I is my conditional participation fee. So buyer I agrees to pay this once other agents report their types. Okay, so independent of whether he wins or not, he pays this Riv minus I. If he wins, then he pays this additional amount, which is the second highest value. If he does not win, then this is the participation fee. So every gross mechanism basically, can be written like this. So I can always write hiv minus I like this, so that it is of this form. Okay. Is this clear? Is this reformulation of the gross mechanism clear?
Is there any intuition behind converting HI to RI?
So the intuition is I just wanted, because the original expression here, if you think about it, if buyer I wins, his payment is hiv minus I, right? Because this term is 0. If buyer I is the winner, then the value of the others is 0, right? So it's hiv minus I. If buyer I is not the winner, then it is hiv minus I minus the highest of the V's. Okay. So I have just translated it so that it looks close, it looks like a Vickrey auction with a participation fee. And the translation is done by just adding this max of j not equal to I vj.
Okay.
Okay. So if you just translate this hi term by this max of j not equal to vj, then basically you will get this new interpretation of the gross mechanism. Okay. So what this?
So why? Yeah. So why are we not directly defining HI to be RI plus max of VJ?
That's all that I'm doing. That's all I'm doing. Okay. I'm just so here if you see hiv minus I is equal to riv minus I plus max of vj. Right?
Yeah, we can do that, right? Because it is only dependent on other people's.
Yeah, but all
value.
I'm trying to say is that is without loss of generality.
Okay.
Okay, so any hi can be converted to an riv minus I plus this. Yeah. Any other questions? Okay, so all this, all I have told you is that every gross mechanism is a Vickrey auction plus a conditional participation fee mechanism. Okay, Vickrey auction plus a conditional participation fee mechanism. Okay, and basically that's what we are going to use in this. Okay, so the result, let me go to the result first. Okay, so the Kramer-MacLean result basically says that an information structure admits full surplus extraction if for all I there exists no rho I. So this is a function, okay, rho I, with rho vi not equal to 0 for some vi, such that this system of inequality equations is satisfied. Okay, so the condition is quite a mouthful because it requires you to verify this existential qualifier that you need to check if there exists a rho I which satisfies this equations. Okay, and from our linear algebra, we know that there are standard tricks to verify if a certain system of equations have a solution or not. So basically, it is pointing to some kind of a full rank condition on these priors. Okay, so I'm putting this full rank in quotes because it's not exactly a full rank condition, because the set of constraints might be more than the number of constraints might be more than the number of variables, and so on and so forth. But all you need to think right now is that the condition on the priors is basically the priors need to the priors need to be such that the only feasible solution of a system of equation is basically all zeros. Okay, so that's basically the requirement. Okay, so we are going to prove this result, and before I prove it, let me make quick observation that why independent priors cannot satisfy. Okay, so why independent priors cannot satisfy this condition? Well, if priors are independent, then this particular term is independent of vi. Okay, so I can always take this outside. So this will just be pi v minus I. And then because these priors are always positive, then the condition boils down to this being equal to 0. Okay. So, so remember the condition says that there should exist no rho I with rho vi not equal to 0 for some vi. But I can always construct a row system which sums equal to which sums to 0 trivially, right? With some positive and some negative elements. Okay, so with independence, I can never satisfy this condition. Okay, that is, there will always exist rho I with rho vi not equal to 0 for some vi, so that this is satisfied. Is that clear? Yeah, so independence means that we are just taking this pi out of the equation in this system of equations, and so we can always satisfy it trivially. So this theorem basically gives a sufficient condition on the priors such that we can admit full surplus extraction, and the mechanism used is a Grove's mechanism. And what we are going to show is that the theorem is going to show is that there exists a participation fee. So there exists these RI V minus I's such that the full surplus can be extracted if this sufficient condition is satisfied. Okay, if the prior satisfy this condition, then you can always set up those RI V minus I's so that full surplus can be extracted. Okay, so that's the bottom line of the paper, and the proof is quite simple, but it uses an important result from linear algebra or linear programming. I don't know if you are aware of this result. So this is called Farkas lemma. It's used quite extensively in linear programming techniques. So the reason I have written a version of this, although the full version I'm not going to use it, is because it's an important tool to remember, and you can use it in some other kinds of research also. So without going through the notations and so on, what this is saying is that uh, it's saying that a system of equations have non-negative or even without non-negative a solution if and only if another system of equations has no solution. Okay, so F is one system of equations and G is another system of equations. So the Farkas lemma says that F is non-empty if and only if G is empty. So why is this useful? Well, uh, in many settings, it may be difficult to verify whether a particular system has a solution or not. But this particular, the G system, which is called the Farkas alternative, may be easier to verify if it has no solution or not. Okay, so in that sense, the Farkas alternative is also called the dual system, is an easy certificate if the original system has a solution or not. Okay, and the proof of this, you know, if you Google Farkas lemma, you will find a wiki entry of this or something. But the proof of this is not at all difficult. You need to spend about 45 minutes looking at it. But basically, it uses separating hyperplane theorem. I'm sure all of you are aware of separating hyperplane theorem. Do you know separating hyperplane theorem? How many of you don't know it? I'm sure in micro 1 it has been taught.
Yes,
Even
sir.
in micro, even in the game theory lectures.
Oh really? Did I teach?
Game theory too.
Oh, game theory 2. Okay, okay. Okay, so basically this is a direct application of separating hyperplane theorem. Of course, to apply it, you need to think exactly in what space you should apply and so on. So that's basically the trick. Okay. So let me read out exactly what this is. So the F system is basically some m number of equations with n variables. So x1 to xn are the variables. So this is like sum of aij xj equal to pi. So m equations, and there is a non-negativity constraint here. So x has to be Rn plus. Okay, and the G system is basically the m variables. So notice that there are m constraints here. So the variables in the G system is m, and there are n inequalities here, weak inequalities here, and these inequalities are aij yi greater than equal to 0. Okay, sum over all the variables. And then there is this single strict inequality here, which says that sum of bi yi strictly less than 0. So the claim of the Farkas lemma is F is non-empty if and only if G is empty. So if F has a solution, then G has no solution. And if G has no solution, then F has a solution. Okay, so that's what the claim is. The claim continues to hold even if X is not restricted to be non-negative. If X is not restricted to be non-negative, as is the case here, the same theorem will continue to hold. The only change that you need to make is that these inequalities in the G system has to be equalities. So the sum of aij yi has to be equal to 0 in that case. Okay. So in that case, basically, if X is not restricted to be non-negative, then this system of equations has a solution if and only if this system of n equations and this strict inequality has no solution. Okay, that's what the Farkas lemma says.
Do we have to make summation bi yi is equal to 0 as well?
No, not equal to, strictly less than. So that remains strictly less than. Yeah.
Okay, sir.
So here is an example just to get a sense of what we are talking about. So here is a system with 3 variables and 4 constraints, right? So this is the system. So this is my F and this is my G. So this G is also called the Farkas alternative. And what this is doing here is, the first one is the strict inequalities. So remember, it is sum of bi yi less than 0. So what is sum of b? So remember, the set of variables here is the set of equations here. So for each equation here, I have a variable. So y1, y2, y3, y4. And sum of bi yi is just 2y1 plus 4y2 minus 5y3 plus 3y4, is strictly less than 0. So that's the last constraint. And then, as I said, if you don't have non-negativity constraint, these are just equations, and there is an equation for every variable in the F system. So what is the equation? Well, look at the coefficient of x1. So it's 1. So 1 times y1, 2 times plus 2 times y2 plus y3 plus y. This should be y4. These are all y4s. This is a typo. So plus y4 is equal to 0. Okay. And similarly, y1 minus y2 minus 2y3 plus 3y4 is equal to 0. And y1 plus y2 minus 2y3 minus 4y4 is equal to 0. So the Farkas lemma basically says that this has a solution if and only if this has no solution. Okay. So you'll see the usefulness of this result in the theorem that we're going to prove. So we're going to prove that this information structure admits full surplus extraction if and only if, no, it's not an if and only if the priors satisfy this equation. Okay, so that is, there exists no rho I such that this equation can be satisfied. Okay. Right. At this point, I mean, this might look like a very mechanical sufficient condition, but you can think of it as, verifying if a system of equations involving the priors have a solution. And because there are well-known algorithms to verify this, so it's just a matter of inputting the priors into some computer and checking if the priors satisfy it or not. Right? So that's basically the tool. Okay, so at least one interesting aspect of this result will be the mechanism that we are going to use. And so as I said earlier, we're going to use a victory auction with this conditional participation fee. And so the proof of the theorem basically ensures that those participation fees can be constructed so that full surplus is extracted. To do that, let me first remind everyone that the victory auction's expected payoff for every bidder can be computed as follows. So if I'm bidder I and I have type VI, then my payoff is at type profile VI minus I is this, where this is the efficient allocation rule. So this term is VI if I am the winner and 0 if I am not the winner. And this term is equal to the second highest value if I am the winner and 0 if I am the loser. So if I am the loser, then this is, this is 0. If I am the winner, then it will be basically the, the conditional expected value of the highest of the n minus 1. Okay, so that's what this term is. Okay. So whatever that is, let's denote it by U star IVI. And with some change in notation, I'm going to write this term, which is the ex ante expected value of expected utility of agent I from the Vickrey auction. So U star IVI is its interim payoff once he has type VI, but the probability that he has type VI is pi VI, where pi VI is just this, okay? Right. So if you take this particular expectation, then you get the ex ante expected payoff of agent I. Okay. And using this, that this is equal to this, we notice that this can be simplified like this. Okay. So if you just make the substitutions here, then this basically boils down to this. Okay. So just algebraically manipulating. This is going to be useful because what we know from the using the property of the Vickrey auction, we know that somehow. So let's go back to the full surplus extraction definition. So let me go back here. So remember, for full surplus extraction, I need to construct a mechanism whose expected payment is equal to this particular term, expected highest value. But I can always write the expected highest value as a function of the terms of a Vickrey auction. So that's what I'm doing it here. So that's basically this is equal to, remember, max of VI is exactly sum of I in N Q star I VI V minus I VI, because in the Vickrey auction, I always allocate to the agent who has the highest value. So this would always be equal to max of VI, right? So this equation you understand. And then this one, the second equation, follows from our earlier algebraic manipulation. So if you now just substitute this here, so this term, if you substitute using this, so remember this is equal to this plus this second term. Okay, so I'm just using that to get here. So intuitively, what this is saying is that the expected highest value is equal to the expected payoff of the bidders plus the expected payment of the seller, which makes sense, right? Because the expected payoff of the seller is basically expected highest minus expected second highest, and the expected payment is expected second highest. So the expected, these two sums basically give you the expected highest value.
Can you please explain it again?
So algebraically, you can just verify it, but all I'm saying is that in the Vickrey auction, okay, so the expected payment of the bidders is basically the expected second highest value, okay, and expected utility of the bidders, okay, ex ante utility of the bidders is basically expected highest value minus expected second highest value, right? Because the highest value at every type profile, the total utility is the highest value minus the second highest value. So the expected utility is just expected highest value minus expected second highest value. So these two things, when you add it, you just get expected highest value, which is this. Okay.
Yes, sir.
So all these algebraic manipulations is doing that. Okay. So because our earlier condition was that full surplus extraction is equal to the sum of payments, right? Full surplus extraction is basically sum of expected payments is equal to expected highest value. We can rewrite that as full surplus extraction is possible if and only if there exists a DSIC and IIR mechanism such that this is equal to the expected payment in the mechanism. Okay, because the expected highest value is this. So this is equal to the expected payment in the mechanism. So that's just a rephrasing of the problem, basically. Okay. the reason I'm doing this in this way is that now the right hand side has Vickrey auctions terms, and we are going to augment Vickrey auction with some conditional reserve prices, conditional participation fees. And so it's useful to keep this in mind. Okay. So what we want to what we will do is that we will construct this new mechanism QP from Q star P star, the Vickrey auction, such that this constraint is satisfied. Okay, that's what we're going to do. So how are we doing that? Okay, so we now construct this new Groves mechanisms by specifying Ri in this way. Well, the Ri's are chosen, okay, such that the sum of the expected RIV minus I. So this is like the expected participation fee of type VI. So if you're type VI, okay, the participation fee that you're going to pay is RIV minus I. And the probability that others have type V minus I is pi V minus I, given that your type is VI. Hence, this is like my expected participation fee. And that's exactly equal to U star I VI, the expected payoff in the Vickrey auction. Okay. So basically first we need to ensure that I can construct such a participation fee. Okay. It's not clear that I can construct something which satisfies these equations. And that's where the Farkas lemma comes into picture. Okay, so to be able to construct these RIs is like, to be able to construct, to be able to have a solution to a system of equations like this. Okay, you should think of these XJs as RIs in our problem. Okay, so we are asking whether we can construct these RIs. Well, a sufficient we can use the Farkas lemma. So what is the Farkas alternative? Well, remember we have to write the G system, which is the Farkas alternative. We have to create a variable for each of the equations and write down an alternate system like this. So in this case, what will that alternate system look like? Well, I have to create a variable for each VI, and that variable I'm denoting as rho I VI. And the first one, remember, says that sum of BI, YI is strictly less than 0, right? So that's the first, the second constraint here, that sum of BI, YI is less than 0. So in our system, that will mean that the sum of rho I VI, U star I VI, so BI is U star I VI, sum over that is strictly less than 0. So that's the strict inequality. And then you have these equations for each of the variables, right? So the variables are in the F system are pi V, Ri V minus I. These are the variables, Ri's. And so for each of these variables, I have an equation, and that will basically mean that rho I VI times the corresponding coefficient of the variables summed over is equal to 0. Right? So we can go back to this example. Here these equations were just saying that y1 plus 2y2 plus 3y1 plus y4 is equal to 0. y1 minus y2 minus 2y3 plus 3y4 is equal to 0. So similarly, we write in this a system of equations, which is sum over all vi, rho I vi, pi v minus I given vi is equal to 0. And this has to hold for all v minus I. So we know from Farkas lemma that this has a solution if and only if this has no solution. Okay, we need to show that 2 and 3 cannot be satisfied together. Okay, if we can show that, then that is equivalent to requiring that this has a solution. Okay. So for this, we know that what are we given? Remember, this 3 is exactly our condition, the sufficient condition given in the theorem, right? So we know that this condition can only be satisfied if all the rho i's are equal to 0. Yes, so everything is equal to 0. That's the only time this can be satisfied, because it says that there exists no rho I so that this can be satisfied, non-zero. So the only way 3 can be satisfied is if all the rho i's are equal to 0. But if all the rho i's are equal to 0, then the left hand side of 2 is equal to 0. So 2 cannot be satisfied. Okay. So 2 cannot hold. So 2 and 3 can never simultaneously hold if the sufficient condition of the theorem is satisfied. So that means that Farkas alternative has no solution. So that means that there is a solution to this. Okay. So the place where we have used our sufficient condition basically ensures that we have this RI functions, so that the expected participation fees is exactly equal to the payoff in the weekly auction. Okay. So
Is this unique?
not necessarily. So there might be multiple solutions to this. This just says that there exists some RI, okay, but there might be more than one RI.
So if the participation fees is not unique, how can we say it will be maximum?
What will be max? Remember, the participation fees for each V minus I may not be unique, but in expectations, the you'll see that the expected payment is equal to the expected highest value. So all of them will satisfy that. So this constraint will hold.
Okay, sir.
Okay. For each V minus I, it might be different, but expectation they will be the same. Okay. So clearly, by specifying this new RI on top of the Vickrey auction, I am just defining a new Groves mechanism. So it's DSIC and efficient. Okay. So since payment of agent I in the Vickrey auction, is U star. Is the Vickrey payment, and I'm just adding this RIV minus I. So the expected payoff is just U star IVI minus the expected, conditional pay participation fee, and by construction, this is equal to 0. Okay, by construction, this is equal to 0. So the expected payoff of every buyer at every type is equal to 0. So interim IR holds by construction. Okay, so in fact, interim IR holds in a very strict sense that we are giving everyone exactly equal to 0. Okay. And from this, it's clear that we can extract all the surplus because the expected payoff of every buyer is 0. So hence it must be the case that the seller is taking away all the surplus. Okay. And basically this algebraic manipulation here is just showing you that. Okay. So this is the expected payment from this new mechanism, but the payment in the new mechanism is just RIV minus I plus P star IV, the Vickrey auction payment plus this participation fee. And by this particular formula, okay, you can write this RIV minus I expectation in terms of U star I, okay, and this P star I remain as it is. And remember, that's what we had shown here, that we just need to, for full surplus extraction, we just needed to show this. Okay, so that's basically, we have shown that full surplus extraction is possible.
So, sir, we have to select a Q and P pair, and Q is selected as the highest value agent gets the
Yes,
object
yes,
and gets.
yes. And P is basically the Vickrey payment plus this RIV minus I, which is a solution to this system of equations.
Okay, sir.
Okay. And basically the condition given in the theorem ensures that there is a solution to this system of equations.
Okay, sir.
Okay. It's probably intuitive to look at this in a two-agent setup because uh, things look a little easier and transparent here. So suppose there are two agents, 1 and 2, and their types are, type spaces are v1 equal to v2 equal to x. In fact, for simplicity, you can assume that capital X is just 0 and 1. So there are just two types, 0 and 1. Okay. So then what is the Kramer-MacLean condition? Well, the Kramer-MacLean condition says that there exists no row. I mean, for every agent there is a row I, but remember this Kramer-MacLean condition has to hold for every I. Okay, so you need to verify for every I, but because the agents are symmetric here, their type spaces are the same, so you can basically uh, uh, assume that uh, you just look at one of the agents. Okay, so this is one of the agents, let's say agent 1. Okay, so for agent 1, what is the condition? Well, you can't find a row, so this is agent 2's type is I'm writing it as small x, and agent 1's type is y. So this is the conditional no, did I get this wrong? Okay, so I got this wrong. So this should be the other way, right? So this should be phi x given y. Okay, I'm sorry. Right, so this should be phi x given y. So y is the type of agent 1. Okay, so the conditional probability that agent 2 has type x is phi x given y times rho x, and summation of this will define one equation for type y. Okay, and then you basically do it for each of them, and it will define like a finite set of equations. And because the number of equations is the same as the number of variables, in this case this will be equivalent to requiring that this conditional probability matrix has full rank. Okay, so it's a full rank condition in this particular case. If you have more than two agents, and this type spaces are not the same, then basically yeah, or not of the same cardinality, then it's kind of a generalization of this full rank condition. Okay, and more broadly, it's basically a condition which ensures that certain system of equations has a solution, and so we know that from our linear algebra how to verify that.
Sir, this CM condition is only a sufficient condition.
It is only a sufficient condition.
So in case of independent priors, this condition does not hold, we have seen. So
yeah,
how can we say if it does not hold, then such FP pair cannot exist basically? It may exist because it is not a necessary condition.
right. No, that's true. So that result does not say that we cannot do full surplus extraction. Full surplus extraction in the independent case. I agree with that. So, but that follows already from Myerson that the maximum that we could achieve is not full surplus extraction, right? Myerson has shown that you have to give some information, right? So I only made that comment to make sure that this is not a crazy condition that, so you can easily see that independence does not satisfy. Of course, that doesn't mean that there does not, it's a sufficient condition. It doesn't say that independence will have full surplus extraction, will not have full surplus extraction. That basically follows from Myerson's result. Yeah, you're right.
Sir, at some type profiles, the payment can be more than the maximum type. So how is that possible?
Absolutely. So let me comment on these things. Okay. So first is, the Farkas lemma and everything that we have done here, the proof only works for finite type spaces. Okay. But there is an extension of the result to infinite type spaces also. And the extension was done in this paper by McAfee and Rennie in 1992. Okay. Second comment is that the theorem uses BSIC as the solution concept, but the paper does have a version of the theorem with Bayesian incentive compatibility also. Okay, and a weaker sufficient condition is given. So if you allow for a weaker solution concept, you can get a weaker sufficient condition on the priors. And the third point is what you're saying, that the conditional participation fee can be higher than value for some agents who do not pay. Okay, so basically, even if you win, basically the conditional participation fee can be higher than the value. So all this is saying is that CM mechanism fails ex post IR. Okay, so it may fail ex post IR. So agents, even if they don't win, they may end up paying something. Even if they win at some types, they may end up paying more than their value. Okay, so it may fail ex post IR. As an exercise, you may want to take a particular kind of prior and construct an example where ex post IR is fails, but it's well known that by looking at the mechanism, it's quite clear that it will fail ex post IR. Okay. However, notice that the interim utility of every agent of every type is equal to 0. So IIR will be satisfied. So
can we make some adjustment in this mechanism to make sure that along with IIR, ex post IIR is also satisfied?
So here is an exercise. You can try to show that it's impossible to achieve full surplus extraction with ex post IR and BSIs. You can try this as an exercise. It's not possible to achieve a full surplus extraction.
And sir, in the McAfee and Rennie paper,
yeah,
the results significantly change, or they are just the continuous time version?
The continuous version of this. So the condition looks more complicated, but it's a continuous analog of this system of equations type condition.
Okay.
Okay. But they also use similar interim IR and BIC and DSS. Yeah. The sufficient condition requires priors to be correlated, but the condition is quite synthetic in the sense that, to verify whether a particular prior satisfies that condition, you basically have to specify whether a system of equations has a non-zero solution or not. Okay, so that's what makes it a kind of a mechanical condition. Okay, so many theorists believe that it's very, very cosmetic theorem, but it's also important to realize that such theorems are important because they set a benchmark. So they basically, that even though it may be very difficult to verify whether conceptually at least verify whether a particular class of correlated priors satisfies or particular correlated prior satisfies this condition or not. It's important to realize that there is a class of priors for which this condition will always be satisfied. Okay, and there is a huge literature now in economic theory to show that basically the set of priors. So think of all possible priors. Okay, so the question is how large is the class of priors which can satisfy this equation 3, right, or this sufficient condition. So amongst the class of all priors, how large are the class of priors which can satisfy this? Well, if that class of priors is very, very small, then this is not really saying anything, because it's just saying that for very small class of priors, you can extract full surplus. But not surprisingly, that there is a big the literature has shown that those of you who have taken measure theory, the class of priors which satisfy that generic that system of equations is generic in the class of priors. Okay, so in an appropriate measure theoretic sense. So the independent priors, again, those of you who have taken measure theory, in the set of all priors, the independent priors have measure 0. Okay, so the independent priors failing that condition is already consistent with this statement. But what people have shown that the class of priors which satisfy those conditions is generic in some sense. Okay. Okay, so in that sense, it's a useful benchmark result.
Sir, is the class of prior a convex set?
Yes. Of course, it will be a convex set, because if you, I think, if you take two priors which satisfy this condition, then you can show that any convex combination of that would also satisfy this condition. I think. I need to think more, but I think it's true. So this is not saying that we should not investigate some other interesting priors which may fail those conditions. The problem is that Meyerson's technique totally breaks down with correlation. Okay, so notice that we didn't use any of those characterization and Meyerson technique in improving any of the results. The proof was quite mechanical in this case. Okay, so Meyerson techniques breaks down. So if we were to investigate optimal mechanism design where the Kramer-MacLean conditions don't hold, then we need to invent new techniques and new tools to address those problems. And the literature is silent on that so far. Another criticism of this CM Kramer-MacLean paper is that the mechanism they propose is quite prior heavy, because the participation fees, the way you construct, is basically a solution to this system of equations. And to solve this system of equations, you need to know these priors, right? So it's quite prior heavy. I mean, even if I know that the system of equations, the priors satisfy this condition, to construct the mechanism which can extract the surplus, the designer needs to have a lot of information about the priors. And so that's, in that sense, it's a prior heavy mechanism. So all in all, the CM full surplus extraction theorem is a benchmark result in mechanism design. And anything that we say beyond this would have to be evaluated against that benchmark. Like, okay, so there is a class of priors where we can extract full surplus, but what can we do if we can't do that? So that's basically. Okay, any questions? Okay, so
Sir, what is the visualization of that dual problem?
So the visualization is, so for that I would suggest you look at the proof of Fatka's lemma. So the visualization is basically the dual, the variables in the G system are kind of the they lie in another dimension, they lie in some other space. So it's very difficult to visualize them in the same space. But if you look at Farkas lemma in the separating hyperplane theorem, basically tells you that they are kind of orthogonals of that of the space of F. Okay, so I would suggest that you look at the Farkas lemma's proof for getting an intuition of how those duals look like.
Sir, are there any results giving the class of tires that have the same optimal participation fee or something like that?
Same optimal participation fee?
Yeah, for a certain class of tires, will get the same optimal participation fee. Are there any results on that?
No. So you're saying that this may not be unique. So you want to characterize the entire solution to this. Is that what you're saying?
Yeah, kind of.
No, but you see, this is a linear system. So basically, if you were to think of a linear system of equations, if it has multiple solutions, then basically they can be described by what are called the extreme points. Okay. So if you get a sense of these extreme points, then every other solution is a convex combination of these extreme points. So that's basically the best answer you can hope for.
Okay.
Yeah. Okay, so I'll correct some of the typos that were there and I'll upload these slides. Okay, and so this is the end of optimal auction design, and from the next class we will look at redistribution mechanisms. Okay, so I think I'm left with about 3 to 4 lectures, and that's enough for redistribution mechanisms. Okay. Okay, I'll see you then.
Okay.
Okay, bye.
Sir, how many lectures are left in total?
3 to 4 lectures, I think. So I just want to finish redistribution mechanisms. It will at least take 3 lectures. If it requires the 4th lecture, we will take it also.
Okay, sir.
So I think this was my 21st lecture. So usually the number of lectures is about 26. So that should be it. Okay.
And sir, anything about the exams? Like, will there be take-home exams or what?
We'll think about that. So regarding exams, I have graded your midterms. I will send you your marks early next week. Okay.
Okay.
Okay. Bye.